Hi, folks. Let's talk about vectors. So this is the video recording that goes with the vector math recitation that we didn't quite get to in class. Given our two vectors, u and v, expressed in unit vector form. And I guess we don't need them yet because the first question asks us about a different vector, w. W has specified for us a magnitude, 13 units, and a direction, 157.38 degrees counterclockwise from the positive x-axis. We can find the components using trigonometry. Where w is the magnitude of vector w, so there's no arrow over top, so we mean the magnitude. Vector w is the hypotenuse of a 5, 12, 13 triangle. So those, if you don't round the trig, which I had to do to get it to 157.38, but if it comes out really, really, really close to 12 and 5. Next, we were asked to add, there we go, vectors u and v. Adding vectors goes like we expect it to. This should be reviewed from 231, but we keep the unit vectors and collect the different pieces. And there we go. U dot v. Okay, so the dot product asks about the projection of one of the vectors onto the direction of the other so that we can multiply them as if we were multiplying numbers on a number line and end up just with a number that was signed according to whether we were multiplying two numbers that have the same polarity, like two negative numbers or two positive numbers, or negative if we were multiplying numbers of opposite polarity. So finding the projection of one onto the other, we would use, I'm actually going to write this formula for number 4. The formula originally sort of defined for the dot product is the magnitude of each vector times the cosine of not the angle of either one necessarily, but the angle between them. Now, at the time we get to question 3, we don't know the angle between them. That's what 4 is going to ask us for. So we can leverage this relationship, this definition for the dot product, to express the dot product component-wise. So 3i dot negative 3i. We take the magnitude of thing number 1, 3i, and the magnitude is 3. The magnitude of the second thing, negative 3i, so the magnitude is again 3. And the cosine of the angle between those two things. Well, I hat is the x direction. Negative 3i hat is the opposite direction, and the angle between those is 180 degrees, the cosine of which gets us a negative sign. So we're distributing like we would if these were binomials. We're distributing the dot product across the parentheses. So then we ask for 3i hat dot 2j hat, but the I and j directions are perpendicular to each other. The cosine is 0. That term in the distribution disappears. Same with I dot k, same with j dot I. The next term that isn't 0 is 4j dot 2j. Well, now they're both in the positive j hat, they're both in the positive y direction, so we're just multiplying the magnitudes. And there would be a k hat dot k hat term. That one would not be 0, but since vector u has no z component, we don't have a term to distribute, and we're done. Note that the result here is scalar. It has the dimensions of whatever the units of vector u are times whatever the units of vector v are. But since we don't have any unit specified, it's just, I guess, square units. But it is just a number, and it has no directional content. The fact that it's negative indicates, think about the cosine of the angle between, indicates that vector u and v are more anti-parallel than they are parallel. In other words, the angle between them we expect to be greater than 90 degrees. Well, all right, so let's see if that's what we get. The magnitude of vector u, finding the magnitude means we square the components, add them, and take the square root. Same story with vector v. Now, the thing is, we know now the result, u dot v. We know that it's -1. So the only thing we don't know is the angle phi between them, which is what we're asked for in step 4. Nine plus 4 is 13. 13 and 25 is 38. And I just gotta, pretty sure it's like 91 degrees or something like that. I just gotta check my math here. Hmm. 91.86 degrees. 5. The magnitude of the cross product. Now the cross product uses a slightly different mnemonic for multiplication. Instead of talking about the projection of one onto the other so that we can multiply as we did for a number line, instead we think of a grid and the area spanned by the two vectors. The sort of what I think of as the definitional cross product representation, U cross V for any arbitrary two vectors would be the one's magnitude times the other's magnitude times the sine of the angle between them in a direction. So this cross product is a vector product. We end up with a vector result, a directional quantity in a direction perpendicular to both. So that's the unit vector in the perpendicular direction, perpendicular to both U and V, according to a right-handed coordinate system, the right-hand rule. Now that's if we need to sort of conceptualize the direction. In step 6, we'll be asked for the vector result, which will have some direction, but it's a little bit trickier to specify the direction of a vector in 3 directions. We need an azimuth and an elevation. It's a little bit harder, not that it can't be done, but it's a little bit harder to specify the direction. This representation is most useful when we have some symmetry involved, some foreknowledge of how the result's going to look. So we'll, in step 6, we'll get a vector result, and that'll be that. For 5, though, since all we asked for is the magnitude, that's all we need. And the angle between vector U and vector V is the same as it was in step 4. $30.8. All right. The actual cross product is almost always found using a component-wise multiplication. I cross J is K, but because we're using a right-handed system, J cross I is backwards in the system and gets us negative K. So we end up with this sort of alphabetical cycle, I to J to K, back around to I to J to K to I to J to K. If we go the other way around, then we introduce minus signs. It's not that we can't look up the formula for the components of the cross product. X, V, Y minus y, v, x. U, y. The y component of vector u is 4. The z component of v is -5. So that's -20. There is no z component of vector u, so that's a 0 plus the z component of vector, that's 0 minus the x component is 3. The z component is 2, so that's 6. Right? Yeah. Plus k u x vy. So oh, wait a minute. Ux was 3, z, hold on, z was -5. So that's -15. This is 3 times 2, 6 minus 4 times -3. -20i plus 15j plus 18k. And just for completeness sake, if we check the magnitude of this, do we get 30.8? Yes, we do. Okay, cool. It's an 8. Okay, page 1. Moving on to page 2. Wait, what is this about? The potential energy of a pair of hydrogen atoms. Potential energy, what is the force that one exerts on the other? Oh my goodness. If we have the force associated with a potential energy function is expressible as the negative gradient of that potential energy function. The gradient operator has three components that act on function u. Only one of those is non-zero. The rate of change of function u with respect to y and z are both 0. So the only one that survives is x. Negative I hat del by del x of negative c sub 6 over x to the 6th. Let's make that c sub 6 x to the negative 6. Negative exponents are our friends. Negative I del, well, we can take the derivative. The rate of change, x to the negative 6, so we decrement the exponent and put it over the new exponent. So x to the negative 6 become, wait, negative 6 comes down, so that's 6c6 x to the negative 7. That minus sign out front is still there. And that's the force that one atom exerts on the other. The minus sign indicates to us that it is attractive. And we know that, suppose we put one of the hydrogen atoms at the origin. The other one is some distance x away. Let's say it's a positive x value. So the magnitude of this component would be positive, x to the 7th, with a positive x coordinate. And then the minus sign it directs us in the negative x direction, which is towards the original hydrogen atom at the origin. Attractive. Cool. Same story with number 8, or at least similar story. A small block with a mass, the net force is described by the potential energy function stuff. What are the magnitude and direction of the acceleration? Okay, cool. So if we know the net force, because we have the mass, we can find the acceleration. And we can find the force by doing what we just did with the gradient operator. Joules per meter squared, joules per meter cubed. So this is all base metric, no like kilograms or nanometers or anything like that. So I'm going to trust that the units work out and not write them. Remember that partial derivatives ask for the rate of change with respect to this variable, holding the others constant. So when we're asked for the rate of change with respect to x, pretending that y is constant, well, that whole second term there is just constant then. So its derivative is 0. Which means we get negative I hat (11.6x) (3) comes down 10.8 y squared into j. Okay, so that's the force. The acceleration at a particular point. (0.3 meters, 0.6 meters would be the negative, or the net force at 0.3 meters, 0.6 meters divided by the mass. So we evaluate the force at those 2 points. So that's 11.6 times 0.3. 10.8 times 0.6 squared. 87 and 97.2 meters per square second because we started with base metric units to begin with. The magnitude and direction, okay. Magnitude is the square root of the sum of the squares. (130.4 meters per second squared). At the angle, let's see, the x is negative, the y is positive, so we're in quadrant 2. But when we ask for the arctangent to find the direction, y over x, we're going to get an angle that's actually in the 4th quadrant. And we need that reference angle. So the actual result in standard, like conventional form is 131.8 degrees counterclockwise from the positive x-axis. Okay, so we've talked now a little bit about the gradient operator. The gradient operator is expressible as a vector operator with components, like we just saw. We also talked just now about the dot and the cross product, which multiply two vectors, or at least find the result of one acting on the other according to the dot or cross product formula. So there's absolutely no reason then that we couldn't write gradient vector dot, gradient vector operator dot some other vector field. And in fact, that's what's written here. We call that divergence. So this is del dot E, which say divergence of E. That's the end of the new stuff. The rest of this is entirely straightforward. Suppose a vector field is given this way. Find the divergence of that vector field. The rest is somewhat mechanical. The dot product does what we need it to do, and the vector operator, the component operators of the del vector act on the assorted components. All right, so let's see what I'm talking about here. E0 x over I hat plus okay. Just like we saw with the dot product of u and v, there are three possible terms that are not zero. The I.I, J.J, or K.K. So in this case, we have I.I and J.J, just like we had on the first page. Okay. How would you like to differentiate? Capital E sub 0 is constant. We can pull that all the way outside. Okay. Product rule. The first thing times the derivative of the second thing with respect only to x, holding y constant. So that's negative comes down thing to the negative 2x plus the second thing times the derivative of the first thing, which is just 1. Plus, now, the second term, the second derivative, I mean, has exactly the same form. It's just y instead of x. So I think it's going to end up identical, just with y in the place of x. So we've got the first part of the product, negative 1 x squared plus y squared, negative 2 2y plus, again, x squared plus y squared, negative 1 times 1. So in the first term, the x's cancel. And let's see, so we got x, x, and then in the other, I guess the third term will have y canceling y. So we have negative 1 over 2 plus squared, no, 1 over squared plus y squared plus negative 1 over squared plus y squared squared, 2 plus 1 over x squared plus y squared. I don't see a good simplification here. I mean, there's two of this. There's two of both of these terms. I guess we could find a common denominator. But that's a result. In a similar way, we could ask for the curl, which is the cross product of the this del vector operator. I guess the gradient operator, but we're going to allow it to act on a vector field via the cross product. Let's call it curl. And to avoid this recording becoming too much longer, I'll stop at a certain point. For now, I'll use the sort of rule that I wrote down for the regular cross product. Put the components in order that way. the y component of the del vector is just the partial with respect to y of the z component of vector b, but there isn't one. The partial with respect to z of the y component, but the y component of vector b doesn't depend on z. So that's gone. The partial with respect to z of the x component of vector b, but again, that is 0 because it doesn't depend on z, minus the x partial of the z component of vector b, but there isn't one. So again, that vanishes, plus del by del x of by minus del by del y of bx. And there is that magnitude b sub 0. I'll just put that all the way out front. And at this point, we're back manipulating something that looked very much like what we were manipulating a second ago for part A of number 9. So I'll stop here. The Gauss's law recitation aims to contextualize the divergence and curl operations sort of conceptually. What exactly do these things do? But this, writing it this way, we do have the means to calculate it. So I'll leave it there. Thanks, everybody. See you in class.